This is Chapter 3, Problem 10. This is a good review of components and how you add vectors using their components. We've got a picture here of a bird watcher meandering, or we're going to have a picture here of a bird watcher meandering through the woods. And the general directions that they go some distance east, and then they go some distance south, and then they go north of west. So I'm going to draw that here, and it's 0.5 kilometers due east. So here is my 0.5 kilometers due east. And then it says 0.75 kilometers south. So make that arrow a little longer. So 0.75 kilometers south. And then they go at 35 degrees north of west. And I'll just make it look like that. A distance of 2.15 kilometers. So I'll make that a little bit longer. And I didn't really draw this exactly to scale, but an important point here is that when you walk east and then south and then some direction northwest, you are not necessarily back where you started. So this is not going to make a triangle in all likelihood. We could add this with vector stuff and do some stuff with law of sines and law of cosines and things like that, but I'm going to do it with components because that's the way that you're probably going to want to attack the problem. And sometimes on future problems, it makes your life easier if you do it that way. So let's take a look here. This is already in the x direction. I'm going to call up and right positive. This one's already in the x direction. This one's already in the y direction. This one will have to make find the components up. So I'm going to go ahead and deal with that one. I'll draw it over here a little bit cleaner, not to scale. And it was 35 degrees north of west. So here's the west direction. There's 35 degrees north of west. And it had 2.15 kilometers for the overall length of that vector. So let's break that into its components. I'll draw one here. Here's the x. And this will be a little messy. I'm going to cut through my 35. So look here right now. There's the 35. There's my y. So we've got x and y. So the x component will be the adjacent, and the hypotenuse will be the two sides we're dealing with. So I'm going to write cosine 35 degrees equals the adjacent, which was my, what should we call this? We've got three vectors. What did the key do? They called it vector A, B, and C. That works. So let's call it A, B, and C. So vector A, vector B, and vector C. So cosine of 35 degrees will equal the x component of C, as that's the adjacent, over the hypotenuse, which is 2.15 kilometers. And I'll get that CX is, if I grab a calculator here, we've got, make sure we're in degree mode. We are. So 2.15 times the cosine of 35, we get about 1.76 kilometers. And if x is cosine, y should be sine. Let's double check. So for the y component, that's opposite of this angle, and there's the hypotenuse, so it is sine. So sine of 35 degrees equals the opposite over the hypotenuse. So cy will be 2.15 times the sine of 35, 1.23. And if we think about 35 degrees, if that's 45, go to 35, or way less than 45, the x should be bigger than the y, in this case just a little bit, and the x is just a little bit bigger than the y. So didn't make any mistakes flipping those trig functions or accidentally in radians. So we've got our cx and our cy. And now what the question asked for, this was just all the setup. You always break things into components, draw a picture. The question actually asked for, determine the magnitude and direction relative to due west of the bird watcher's A, displacement. We're looking for displacement. And B was average velocity. So we're looking for our average velocity and our displacement. So those are the two things we're trying to find. And both of those are vectors. Well, one's an average, but they're still both vectors. Let's go ahead and get the displacement first. So again, I can't just figure out, we're looking for what this is right here, but I can't just draw that and have, it's not necessarily a triangle, right? It's not just an extension of that line. It could be here, it could be here. I mean, it could be really anywhere without me doing the actual to scale with a protractor and ruler. I'm not sure. So I'm going to go ahead and do this with components. So let's add everything up. So I'll say displacement in the x direction. I'm going to add up everything in the x. So A, and I call it up and right positive. So A will be Now I'll write the variables here. So we'll have the displacement for A, and I'm using D's for displacement. That's not real standard, but we'll go ahead and do that here for chapter 3. So displacement of A, because that's all in the x direction, plus my CX will be my x component of my total displacement. So we've got displacement A is 0.5 kilometers to the right, so that's positive, and then CX, oh, I need to add my signs on my vectors. So CX is to the left, so negative. And I could have added that down here, but really it's probably best to add it right here as you're calculating it. So X is to the left, so that's negative, and Y is up. So 0.5 minus 1.76 kilometers, and that will give me 0.5 minus 1.76 should be 1.26, right? Yeah, so negative 1.26 kilometers is my X component of the displacement. So now let's go ahead and get the Y component of the displacement. And the Y component will be add up all the Y stuff. So we've got the Y component of C and this 0.75 kilometers, which is down, so that'll be negative. So I'll call it DB plus CY of negative 0.75 kilometers plus our 1.76 kilometers. So we're going to get, what is that, 1.01 kilometers for our displacement in the Y direction. So there's our displacement in the Y direction. Sorry if that was cut off, but here you go. Okay, so we have the X and Y components, and we want the overall displacement. Now we got to put them back together. I'll just go ahead and do that. Let's make a little box here. Let's go ahead and do that stuff right here. So we'll just have drawn the whole thing. Now that I know what it looks like, it's left and up, which I would have expected looking at that. But we got left part, we got an up part. We're going to go from, zoom in here a little bit, we're going to go from tail to tip. So we're looking for that. And we also need the theta. We need both of those. So here's my dx, here's my dy. So Pythagorean theorem and tangent. So my overall d here, my displacement, the magnitude will be 1.26 kilometers squared plus 1.01 kilometers squared. Remember, there's a squared over here, so I'm going to square root both sides like that. Just using the Pythagorean theorem to find the third side, and definitely think I got good for this. So 1.26 squared plus 1 squared 0.5 power, so 1.61 kilometers. And let's go ahead and check to make sure that's what they got over there. Oh. Either the key's wrong or I grabbed a wrong number. Let me go back here and take a look. We got 0.5 east. Yes, I have that. 0.775 south. 0.75 south, we got that. And 2.15 north of west. Or I did order of operations, hold on. 0.26 squared plus, it's in parentheses, 1.01 squared, 0.5 power, 1.61, and they're getting 1.35. Which component are they different on? They're different on the 0.48, and I have 1.01. 0.7 south. The other one's up. Oh, yep, there's my mistake. Right here. Just should have 1.23. I grabbed the x component instead of the y component. I have cy right here. Cy is right here, and it should be 1.23, which will then change this. So 1.23 minus 0.75, we get 0.48. Yep, now we have the same thing they do, so 0.48. Just grabbed the wrong number. Sorry, not a big deal. I had the correct cy here. Just to double check, make sure you're substituting the correct value. Simple mistake. And that'll change this and this. This will be 0.48. Same exact process. I just grabbed the wrong number. The physics was fine. And now our displacement, I'll just use their number there because we've got it the same, 1.35 kilometers. So there's our 1.35 kilometers. Now we need to get our angle. So tan theta equals the opposite, which is our dy, 0.48 kilometers, over our adjacent, which is, let's double check here, opposite dy. So there's our dy over adjacent, which is our dx, 1.26. Take the inverse tan on both sides, and we'll get a theta of, let's see, inverse tan of 0.48 divided by 1.26, getting about 21 or 20.8 degrees. And that's what they have, 21 degrees, and that is north of west. So if we look right here, we are to the north of the west direction, the way I've drawn my triangle, so I'll write that north of west. So that's the displacement. I'll leave the velocity to you if you need help coming after school, but it's average, so it shouldn't be too complicated. You've got your overall magnitude of your displacement. You just need to take now into account that it is a trip of 2.5 hours. Their final answer is in kilometers per hour, so don't overthink it. If you need help, though, come in for part B. That's it.